Okay, so in the last few lectures, we have been trying to understand the semiconductor basics. In the last lecture, we tried to put P and N type of materials together. After putting the both materials together, we found that across the physical contact between the N and P materials, we can see that there exists a concentration gradient, and because of the concentration gradient there is a transfer of charge from one side to another side, and there becomes something called as exposed charges on either side of the physical contact point. Okay, so this is the physical contact point here. So on one side, from we can see positive charges. These are the donor ions on the N side and acceptor ions on the P side. So because of these uh, charged ions, we can see an inbuilt electric field, and because of that we see a potential difference between this also to exist. So the region in which this potential variation is going to happen is the region in which we see these exposed charges. Because of the existence of the electric field here, there is no mobile charge carriers which can stay in this. Because of this electric field, this applies a force on those charges and they are just swept across the region. So we can see that holes will be pushed in the direction of the electric field. So the holes are confined to the P region, whereas the electrons feel the force opposite to the electric field direction, and so electrons are going to confine in the N region. And in between this region, we don't have any mobile charge carrier, so this region is depleted of charge carriers and mostly called this as a depletion region. So this is what the depletion region is.
सर
Yes,
हेलो सर इसमें इलेक्ट्रिक फील्ड कांस्टेंट रहेगी इन बिटवीन द डिप्लीशन रीजन
electric field, how? No, 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 it is not going to be constant. Okay, so in any region, if you choose a smaller region, you will be know from the law of physics. Okay, suppose you choose a region like this here. So in this region, you see only these charges. Okay, in this region, you see a larger charges, and in between, actually, in the middle region, you can see that these charges are separated by a small distance, and so on. So you cannot say that the electric field is going to be same constant, okay, throughout. This is going to change. Already we have seen in the last lecture, okay, that electric field is going to change in this way. Okay, so already we can uh, take the help of the Poisson's equation here and solve that. This is the Poisson equation. We can solve this to find out the electric field here, and the electric field is here plotted. So just at the physical contact point, okay, in the middle of the junction, we see the electric field to be the maximum, and as we move away from this, the electric field decreases and becomes zero. Okay, so electric field essentially is zero outside this depletion region and maximum in the middle. Okay, so already we can see all these things. Okay, so that is not constant. Okay. So the interface in between p and n type material is called the p-n junction, and in the middle we have the depletion region. Across this depletion region, we have a kind of potential difference, which gives rise to something called as potential barrier. Okay. So that tends to stop the flow of the charge carriers across it. So the barrier potential for silicon is in the range of 0.6 to 0.7 volt, whereas for germanium it is in the range of 0.2 to 0.3 volt. And as temperature increases, this potential barrier tends to decrease. So the potential difference across the p-n junction is called
Potential barrier.
potential barrier. Yes. The physical distance from one side to other side of depletion region is called
Depletion region.
Width of depletion region.
yes. Depletion width. So potential barrier of silicon diode is around
0.7
0.7
volt.
and that of germanium is
0.3.
0.2 to 0.3. Yes. So qualitatively already we have understood the working of the p-n junction and the formation of the barrier actually. Okay, let us look at the simple this p-n junction. This is also widely called as a diode, p-n junction diode, and its symbol you can see is shown over here. It is shown by a triangle with a straight line on one side. Okay, so on the n side that is called as cathode, the p side is called as anode, and to just distinguish the anode and cathode we have this. Okay, we have a kind of this triangle pointing in one direction here to just show the direction of current when it is forward biased. Okay, so this is just showing the direction of current here. Okay, so we will see that this simple device allows the current to flow in one direction, whereas it will try to oppose the flow in the other direction. Okay. So that is also there. That is not hard to understand here. We can easily understand this fact by looking at this scenario here. So p-n junction is here. P-n, as soon as we put p-n and type of materials together, there is a formation of p-n junction. Okay, so this is a natural phenomena, and it happens as soon as we put two p-n and type materials or two dissimilar materials together. In general, we can say. Okay, so on one side we will see on the on the p side acceptor ions BC, on the n side we see the donor ions. These things are there. Suppose we apply some potential difference across this. Okay, this is the case when we do not apply any external potential across it. So there are two cases in which by which we can apply the potential. Okay, so one could be like this. Here we apply and another could be like this, we apply the battery. Okay, so only two possibilities are here. So let us say first possibility we look at. So when we look at the first possibility, externally we are applying a voltage as shown here. So this battery will apply a positive potential on this side and negative on this side, and an external field we can see to build up across this PN junction. Okay, as shown here. So this is external electric field which is given by this external battery now. Internally, we have seen as soon as we put at these two materials together, internally there was an electric field formation in the opposite direction like this here, pointing from N side to the P side. But externally applied potential source now is forcing the electric field from the in the opposite direction from P side to the N side. So we can see that there is a contest kind of thing happening between these two electric fields, one that is externally applied, one that is internally induced. Okay, so that which is stronger, that will win. Okay, so in the starting, when suppose we have a potential source V here, sometimes it is also called VD. Suppose VD is uh, say initially equal to 0. Okay, and from 0 it is say increased to some value. Okay, so 0 is equivalent to say not applying any voltage, and if we apply some voltage, then this electric field actually strength is going to increase. So in the starting, the electric field due to the external voltage may be smaller. As we increase this BD, the electric field strength will increase, and at some time it will be just equal to, and after that it will be just greater than the internal electric field. Okay, so nice things happens here. The case when external electric field is say less or equal to say internal electric field, then there is not much change in the behavior as was in the open circuit. Okay, when we didn't apply any voltage, just we put at the p and n type metals together. Only thing is that the strength of electric field is going to decrease. Okay, the effective. Okay, now we can talk about the effective electric field. Okay, so effective electric field may be here because internal electric field is more than this external, so we may write like this here, internal minus external in the direction of the internal electric field. So this is small, so potential barrier is going to be smaller, so some more carriers may be able to cross the junction, but because the potential barrier had decreased, so some more carriers may they have energy enough to overcome this barrier, then they may cross this. So the current due to that may not be that much great because such carriers are less in number. As this external electric field increases, so this effective electric field reverses this direction, and we will see that more number of carriers from P side, they will actually find it easy to go from this side to that side, and on the other side actually also we can say that the electric field which is in the now direction of the external electric field. Okay, so this internal electric field which was resisting the flow of charge carriers, that goes, the effect of that goes. Okay, so it is easy to flow the charge carriers across this region. So that's what we can say now. So electrons will find it easy to move from n side to p side and holes from p side to the n side. And because these are the majority charge carriers, in the p type the holes are majority, in the n type the electrons are majority carriers. Okay, so these majority carriers are flowing and hence the amount of current is going to be large. Okay, so this is what we call as on state, or also be called this as forward bias. Okay, so this is what we call as forward bias. Whereas if we take the second case here, okay, second polarity of the external source, then this is not opposing the internal electric field, but this is going to be in the direction of the internal electric field, and in a sense helping the internal electric field further. Okay, so this is for the second case here. So internal electric field and the external electric field both happens to be in the same side, and so we will see that the barrier grows. Okay, the 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 depletion region will also grow because of this, because we have now more electric field, effective electric field in the direction of the internal electric field. So more potential drop, more potential drop means more potential barrier. Okay, so this is going to further stop the flow of the charge carriers across this region, because it will the charge carriers now will require a large amount of energy in order to cross this region. Okay, so that's why this is called as off state or reverse bias. So this is reverse bias. Okay, so that much easy here. So we can see that a diode ideally conducts in only one direction, okay, and is trying to oppose the flow in the other direction. Okay.
Sir,
Yes.
can you please reshare your screen?
Why?
Because I cannot see it, sir.
My screen not visible?
No, sir. To me, not visible.
Visible, sir.
It may be due to slow network. Okay, I think it is visible to all.
Maybe, sir, it is because
Yeah.
of that slow network. But, sir, can you please once reshare it? Only once, sir.
Okay. Is it visible now?
Yes, sir. Now I can see it too. Thank you.
Okay. So that's why we can say that the diode, okay, this PN junction arrangement that uh, makes the current to flow in one direction and oppose in the other direction, and the first is called as uh, on condition. Okay, so this is first is on condition, and the second is called as the off condition. So this is also called as forward bias and reverse bias. Ideally, this seems to, in the forward bias, seems to act like a short circuit, whereas in the reverse bias, it ideally acts as if it is open circuit, not allowing any current to flow through it. Okay. So before proceeding, okay, looking at this ideal diode characteristics, we may also okay, let us first look at this. Okay, so ideally what we see that as soon as we apply a small forward bias voltage VD, there is a huge current. Okay, so this is the ideal condition. So the current is on the vertical axis here. Okay, with a positive voltage, so VD greater than 0. Even a small voltage greater than 0 makes the current to flow through it. Okay, so this is ideal case. In the ideal case, this barrier voltage is just 0 volt. As opposed to that, as we have seen for the silicon or germanium, it was 0.7 volts and 0.3 volts respectively. Okay, so silicon and germanium, these are practical diodes. So this is just for ideal case here. Whereas if this voltage across this diode is just less than 0, then it acts like it is in the reverse bias and are in the off condition. Okay, so in the off condition we see no current to flow, and even if we increase this BD in the reverse direction, then there is no current sink. So these are the ideal characteristics. So diode acts like open circuit here. So if we look on the other hand, a practical diode is not shown over here. For practical diode, we will see that we need to apply a voltage. Okay, here it is BV, but it is sometimes written as B gamma. The potential barrier. So 0.7 volt for silicon or 0.3 volt for germanium, it could be there, which must be applied across this PN junction in order to make it conduct. So this particular voltage which must be applied, that is called as knee voltage or this potential barrier. So the idea is that due to this internal electric field, we have a potential barrier, and potential barrier is of this polarity here, say 0.7 volt or 0.3 volt, whatever it is. So we need to apply at least BD is equal to 0.7 volt with the opposite polarity. Opposite polarity means we need to apply a external voltage with the same value with opposite polarity to compensate for the effect of this internal potential barrier. So up to this 0.7 volt externally applied voltage, we are just working against the internal field, and we do not make the carriers to conduct till then. So this is what we represent here, that up to this knee voltage or potential barrier, we don't see any current. We have to apply that much to overcome the internal field effect. And after that, whatever the extra voltage we apply beyond this, that will make the carriers to conduct. Okay. So after this, the carriers in the if this is having the ideal characteristic like, then after this may look like to turn on. Okay, will give infinite current say. But also we will see in a moment that this is also not true. We do not have exactly very large current just after this voltage, but rather this current uh, tends to increase gradually like this. We say this is exponential increase. Okay, so already we have seen forward bias. So in the forward bias, what happens we have seen. Just this is graphical representation on the same fact. So we need to bias at, we need to give a biasing voltage greater than this barrier potential to make it forward bias. So overall, if we look at the characteristic here, this is a practical case. In this practical case, we see that the current is not increasing to infinite value, but rather it is exponentially increasing here. And also in the reverse direction, we don't have zero current, but a small finite current we can see in the reverse direction as well. And in this region, okay, in this region, the current is represented by this exponential relation here. This is also sometimes called as Shockley equation, or diode equation. We are not looking at the derivation of this particular equation over here from how it came, but this equation best fits the characteristics of diodes. Okay, that's how we can see. Outside of this region, this equation fails. Okay, this in this region we go enter into the so-called as breakdown region. Okay, and there is a huge flow of current in this region, and it appears as if there is no barrier in the reverse bias. So it is not like that if we are in the reverse bias, then there is no current. Almost there is a small current, very small current in the reverse direction also. But if we keep on increasing the reverse bias voltage, then internal electric field along with external electric field may be too large, and it may give energy to the bonding electrons, or the covalent bond forming electrons, and the bonds may break down, and there may be a generation of electron hole pairs, and the electron hole pairs thus generated may be too large in number, and they may result in a very large current. Also, one can say that the energy of the electrons and holes in the N and P region may become too large due to this field, and may attain too large velocities, may collide with the bonding electrons, and impart energies, thereby breaking the covalent bonds. generating the electron hole pairs and increasing the current. Okay, so there may be two phenomenon. Okay, so the first one in which electric field is too large, so that it breaks the bonds, that is called as Zener effect. Okay, and another is we said that the velocity is too large, kinetic energy is too large, they collide, they impart energy, and due to that energy there is generation of electron hole pairs, that has called another name called known as Lorentz effect. Okay, so there are two actually breakdown phenomenons. One is Zener breakdown and another is Lorentz breakdown. Okay, so these are two breakdowns. Zener breakdown or Avalanche breakdown, okay, may for moderate values of the voltages may be non-destructive in nature. At this juncture, we should also look at the kind of energy band diagram which results in the PN junction. Okay, energy band diagram. So to draw the energy band diagram of PN junction, let us first separately draw the energy band diagram of P and N type of materials. Okay, so for this let us look at this here. So we have say P type material and N type of material separated. Okay, they are not in contact. So in the P type material, if we draw this, then we show conduction band and valence band like this, conduction band and valence band here. We have not discussed, I think, so far, but it is important to introduce one more thing here called as which makes actually the difference between these two materials is that we know that in the P type mostly the electrons are in the valence band, and whereas in the N type mostly the electrons are in the conduction band. Okay, so we see that because of that in the P type we see holes, and in the N type we see the electrons. So actually this particular thing or particular property of the electron or hole residing in the uh, conduction band or valence band, that is shown by a probability function. Okay, so that probability function is widely known as Fermi-Dirac relation. Here we can write here. Okay, for simplicity we can write like this here. So Fermi-Dirac probability function states that the probability of finding an electron at a given energy E is given by this function here. Okay, so we introduce here one energy called as EF here. This is called as Fermi energy. And other terms are conventional. Small k is the Boltzmann constant, and capital T is the temperature, absolute temperature in degree kelvins. Okay, So, so this Fermi function states that probability function states that uh, Fermi energy is that energy, okay, at which if we put this E is equal to EF into this expression, we can see that this probability function becomes half, okay. So this states that the Fermi energy is that energy at which the probability of finding an electron is half, okay. So showing this in the intrinsic uh, semiconductor, we see that there were 8 energy states, okay, 8 energy states, out of which 4 were vacant and 4 were filled, half, okay. So so this is what, so out of the 8 energy states, 4 were vacant and 4 were filled. So we say that this is intrinsic case, okay, and finding the electron was half, okay. So this case is generally shown by putting this Fermi energy in the middle, and this is more generally called as intrinsic Fermi energy, EI, okay. So this is just in the middle, that is, this is Eg by 2, this is Eg by 2, where Eg is the energy band gap. So this is what. Now, if we look at in the P type, then externally we are doing something so that the uh, holes are created, okay. Whereas in the N type, the electrons are created. So electrons are created means more electrons are in the conduction band. To show this fact, the Fermi energy is just shifted towards the conduction band in the N type, and the Fermi energy is shown to be shifted on the valence towards the valence band in the P type. So this is the Fermi energy in the P type and Fermi energy in the N type. Okay. So just okay, from the overview, just we are trying to look at the concept of the energy band diagram.
Sir, why Fermi energy is shifted in P and N type? Please say it again.
Okay, so in the intrinsic, we see that it was middle in the middle because the energy states which were vacant and filled, they are just equal. Half of the energy states were filled, half of the vacant. But in the N type, what we have done, we dope it by dopants, okay, donor type dopants. So donor type of dopants, they give electrons each, okay, one electron. So these electrons go into the conduction band and occupy the energy bands, okay, energy states, available energy states. So more energy states are occupied in the N type, and as we increase this dopant and doping concentration, more number of electrons will appear in the conduction band, and more these energy states available in the conduction band will be occupied. So to show this, okay, we say that it is now the probability of finding the electrons in the conduction band has increased. To show this fact, we have we shift this okay, Fermi energy towards the conduction band. Okay, so it is if Fermi energy level, okay, is more closer to the conduction band, it shows that more electrons are found in the conduction band, more energy states are filled. Yes, what is the question?
हाफ फर्मी लेवल के लिए
Can you repeat? I was not able to hear.
फर्मी टू रहेगी ना या बढ़ जाएगी कंडक्शन बैंड के पास?
नहीं, आई एम नॉट गेटिंग. ओके, योर वॉइस इज ब्रेकिंग. कोई और समझ पाया हो तो बताएं क्या पूछ रहे हैं.
सर वॉइस ब्रेक है.
हाँ, फिर से बताइए, फिर से बताइए. हाँ,
एनर्जी के लिए प्रोबेबिलिटी सेम रहेगी ना इलेक्ट्रॉन की?
नहीं समझा मैं. एनर्जी क्या प्रोबेबिलिटी सेम रहेगी?
यस सर.
किस चीज की प्रोबेबिलिटी सेम रहेगी?
इलेक्ट्रॉन की कंडक्शन बैंड के पास हो जाए सर या फिर वैलेंस बैंड के पास?
No, if you are having more electrons available, more energy states are going to be filled. So how you can say this is just showing the probability of okay, finding the electrons in some energy states. Okay, the more energy states are filled means it is more probable. To just
Okay,
show
sir.
that the fact, okay, to show this fact, uh, it appears that Fermi energy is shifted upside. Okay, actually this Fermi energy is a fictitious energy level. This is not a real energy level. Okay, because uh, one thing it must be clear to all that this energy, okay, is nothing but energy band gap. Okay, or forbidden energy. So none of the electrons are going to occupy any of the energy states in this silicon or germanium in the semiconductors. Okay, so these are forbidden energy states. Energy states are available only below this in the valence band or above the conduction band, like this. Okay, so only these electrons are going to occupy the energy states here, not in this energy band gap. Okay, so this is a kind of fictitious energy which just shows the probability of finding the electrons in the conduction band or in the valence band. If the electron finding if the probability of finding electron is more to be in the conduction band, then the Fermi energy is shifted towards the okay conduction band edge. Whereas if the finding of the electron is more to be in the valence band, then it is shown to be shifted on the valence band. That's it. Okay. So this is just showing here when in the case when the p and n type of materials are put it separated. Okay, they are not in contact. We see that when they are contacted, then something happened, that there was flow of charge carriers across because of the concentration gradient, and then later they become in equilibrium condition and there is no movement of charge carriers. So there is no movement of charge carrier, that means they are in equilibrium kind of thing, and it can be observed that the electrons in the both side, okay, they do have the same energies so that they do not move. Okay, so this fact is shown by this the common Fermi energy. Okay, so it appears as if when we make a contact between these two materials, so it appears as if both sides the Fermi energy has become same, so that there is no transfer of charge carriers across the region. Okay, suppose this is the physical boundary of p and n type of materials. On one side we have p and on the other side we have n. We can now uh, see that across this boundary uh, just something has happened, but far away from the boundary we have seen earlier also that the materials are p type and n type respectively. So let us say that there is some boundary here. Away from this boundary, we have the p type and n type of materials. So say this is p type of material. So Fermi energy is shown to be closer to the valence band like this, and on the right side we have the n type of material. So n type of material is shown to be like this here. So this is EFN and this is ECEB. So these are now in balance here, okay, everywhere. But we can see that there is a discontinuity in the conduction band and the valence band. So conduction band and valence band appears as if they have bending in this transition region, which we have generally called as depletion region. Okay. So whenever there is a energy band bending, we will see that there exists energy barrier and there exists a potential barrier, okay, as well. So potential barrier is there, energy barrier is there, both things are there. Okay, naturally both are same thing. Now here this is the case when we put p and n type of materials together without any other external potential source. Now if we put a potential source also on the p and n side, okay, by some external voltage source, then again we will see the similar thing happens here. And this actually, as already qualitatively we have discussed, that this is a forward bias voltage. Okay, so forward bias voltage will tend to reduce the potential barrier. So actually the potential barrier reduces something like this here. Okay, so potential barrier remains this here as opposed to the earlier value of this thing. Okay, so this is a E naught, E1. So potential barrier is going to change here, reduce because of the forward bias. Similarly, if we apply reverse bias, then we will see that this potential barrier is going to increase. Okay, because of here something like this. Okay, in the same diagram I am just drawing here, so the things maybe seem to be very complicated here. So the energy barrier is now going to be this much. So this is E2. So we can see the energy barrier to increase or decrease depending on the forward bias or reverse bias. So this is because of this reverse bias here. Okay, so just we have seen that how we can draw the energy band diagram. You can practice on your own now. And the drawing of the energy band diagram for the P and N junction in the forward bias and in the reverse bias. So in the reverse bias, DC voltage negative terminal connected to the P region and positive to the N region already we have seen. And in this, the depletion region widens until its potential difference equals the bias voltage. And the majority carrier seats, okay, the correct flow. here one thing is written that minority carrier flow is there. You can give the thought why the minority carrier may flow where as the majority carrier stops. Majority carrier means holes are on the p side, electrons are in the n side, and we see this kind of electric field in this depletion region. So the regions are obvious here. The field is applying opposing fields on the holes and electrons. That's why they do not cross this junction. Whereas minority charge carriers, if we see the electrons in the p region and holes in the n region, and see that if somehow this electron comes in this in the influence of this electric field, or say hole, this comes in the influence of this electric field, then what will happen? This force applies the forces on the holes and electrons in such a way so that the electrons will be going into the n region and hole will be going into the p region. Okay, so we can see that still there is a possibility of transfer of these charge carriers, which are called as minority charge carriers. So minority charge carriers can flow. Okay, so time is almost over, so we shall stop over here. We may continue in the next lecture. Thank you all. If there is any question, you can note down and we can discuss in the next lecture.
Thank you, sir.
Thank you, sir.
Okay, thank you all.
Thank you, sir.
Thank you, sir.